So continuing our study of three-dimensional shapes, we're going to take a look at objects which are going to be called prisms, and then cylinders, pyramids, and cones, see which one's which, and then take a look at something called cross-sections. So this front page is just a bunch of pictures so that you have some visual references to see which object is what. On the upper left-hand side, we see all sorts of different prisms. Notice the prisms have what's called a polygonal base. It's a polygon-shaped base. Notice the difference between what's called an oblique prism versus a right prism. So a right prism is probably more what we are used to. Those are just our boxes or our cheese wedges. That's what this one kind of reminds me of. Versus an oblique prism. In an oblique prism, I kind of think it's like that shape, but in a hurricane, it's slanted over, it's pushed over. Notice that the prisms all have, again, these shapes. So as, for instance, this one on the bottom left is called a triangular prism. It's because the shape of the base is a triangle. Same thing over here, a triangular prism, the shape of the base is a triangle. Then we have things called cylinders. Cylinders now have a curved base. We have just a general cylinder where I have a curved base on at least part of it. Then I get down to here where I have my circular cylinders. And a circular cylinder, again, named by the shape of the base. It's a circle for a base. Again, the difference between a right and an oblique. A right is your typical can standing straight up, the bases being perpendicular to each other. Or when you have an oblique cylinder, that would be like your can that's now tilted. So the bases are not perpendicular to each other. And then we have on the bottom our pyramids and our cones. Our pyramids, notice the difference between a pyramid and a cone. Again, the pyramids are going to have polygons for bases, so I can call this a square pyramid on the right-hand side, where I would call this, since it has 1, 2, 3, 4, 5, 6 sides, I could call that a hexagonal pyramid because it has, again, a hexagon for its base. Cone is a circular base, so as soon as I have a circle for a base, I have a cone. Notice a couple of different parts that are labeled as well. We have a slant height, which is just that. It is the height that is slanted. And then we have a regular height. The regular height is always going to be the height that is perpendicular to the base. So I see in my square pyramid, I can see the difference between the height and the slant height. In my cone, again, my slant height is on the outside. The actual height is on the inside. On the pyramid, because it's just going from the vertex perpendicular to the base, I can see, again, that's going to be a regular height. Slant height is always found on the outside of the shape, where the regular height is found on the inside. So it's just some vocab. A little bit more vocab. Different things to take a look at. It's all labeled on this first picture. We have bases. Those are the two congruent parallel sides. The key word here is there's only two of them, two bases. The edge is just that, it's going to be connecting the bases. All right. It's also going to be the intersection, it says, of two faces. So I can see our lateral faces here. Those are going to be the sides basically that are not the bases. So bases, I have two and only two congruent shapes. Lateral faces are everything else. The edge is going to be connecting two of the faces together and will also connect base to base. The vertex is where I can see the edges all coming together. So I can see edges and I can see the bases coming together at a point. And then we also have something called the slice and a cross section. A slice is what happens when you take basically an intersection that's not parallel to the base. The more important one here is our cross section. And we're going to take a look at a cross section a lot. Cross sections are when you take a slice of the object and it is parallel to the base. So trying to put that vocab to use, we're going to take a look at this picture on the right, and it says using the information, we're going to try and identify at least one base. So we said a base was going to be the two and only two shapes that are congruent, which I'm looking at those being the pentagons. So I could say one of our bases is P1, P2, P3, P4, P5. So highlighting this bottom section down here. Now I could say this other base, if I wanted to, is P1, 2, 3, 4 prime, that top side. by an edge. We have a bunch of edges. The edge we said would take the lateral faces connecting together. It would also be connecting base to base. So I could say something like P1, P1 prime. Okay, I could do the same for P2, P2 prime. A vertex, that's any of the points. So whether it's P5 prime or it's just P2 or something like that, those are going to be your vertex. A lateral face, those are the sides that are not the bases. We have two and only two bases that are congruent to the faces. Those are going to be like our rectangles of this. So I could say one of the faces would be P1, P2, P2 prime, P1. And notice how I had to label that. I have to still label that like I would a rectangle going either clockwise or counterclockwise, but I have to keep it in order. And then the shape of the cross-section. Since the cross-section is always parallel to the base, that means your cross-section should always be the shape of the base. And the shape of the base in this case is your pentagon. Okay. So taking a look at something, trying to maybe throw some numbers, formulas together. It says the following is a right general cylinder. Notice it's a general cylinder because it's not a circle, it's not a polygon, it's just some sort of a curved object. It has a lateral edge length of 8, so that's connecting base to base. So I know that that's a length of 8. It says, and the perimeter of the base is 27, meaning it's going all the way around here, all the way back and around, and that's 27. And it says, what's the lateral area of the right general cylinder? So they're saying, if I were to take a look at this, I want it going all the way around this object. So they're saying, if I could think, take this side here, that lateral edge, slice it open, lay it out flat. They're saying, I want to find the area of that whole thing. Well, if you were to do just that, cut it open and lay it out flat, what you're going to get is a rectangle. So I know that lateral edge is 8. And if they're telling me the perimeter is 27, think about what that's saying. It's going from here all the way around, all the way back and through is 27. So in other words, when we lie it out straight, that's that length of that rectangle. So if they want that lateral area, they're just saying, okay, it's a rectangle. It's length times width. It's 27 times 8. So multiplying that out, that's going to get you 216 units squared. Don't forget your label. Okay. We have a right prism. I don't know what the shape of the base is. It doesn't matter. They're giving me, it says a base area of 5 and a volume of 30. We have to find the height. One of the formulas given to you on your formula sheet is just that, the volume of a prism, which the formula says big B times H, and that big B stands for base area. So we know the base area, so I can plug that into the formula. That's 5. I know the volume. Volume is 30. What I don't know is the height. So by substituting into that formula that was given to us, we can divide through by 5 to find the height. And that's telling us our height now is going to be 6 units. Okay, and again, this is on your formula sheet. You just need to know how to use it. Okay, taking this a little differently, we're going to take a look at what happens if I were to take something and do a rotation around an axis. Okay, so if I'm looking at this first picture, they're saying we have this rectangle, that purple rectangle, and following that arrow, we're taking it and I'm rotating it around an axis. And they're saying, if I do that, what's going to happen? Well, rotating that figure around an axis, we're going to get that rectangle turning into a cylinder, a circular cylinder. What happens if we start with the triangle and we do the same thing? So if we start with the triangle and we do the same thing, we rotate it around that axis. Notice what's going to happen. This point stays fixed. This side, this radius, if I take it all the way around, now I'm going to get a circle on the bottom where this point's really not moving, so that's going to create that cone. Okay, so if we try and recreate this, looking at this rectangle, knowing if I were to revolve this rectangle around this axis, and I'm going to take this point and I'm going to kind of trace it out just like the way it would go. Okay, I would get some object that looks like this. Okay, now keep in mind, not the best artist here, but we're trying our best. Whatever the length of that side is, this should be the same. And notice it's going to happen on the same thing at the bottom. same deal. Okay, so again, that's the length of R, that's the length of R. One thing to keep in mind when you're connecting these, even though I know my picture's slightly off, we're going to see they're going to be perpendicular to each other, just like they were over here. Okay? And now when we have our triangle and we're trying to do the same thing, so this point's going to rotate all the way around. Big thing that we want to keep in mind is it's equally distant. The length of the radius on the left is the same as the length of the radius on the right. That point is fixed and not moving, and that's going to give us a cone. So those are just different types of solids that can be formed when we're taking a shape and rotating it around in a process. Okay, keeping along the lines of this whole cross-section idea, we're taking a look at the figure on the left, which is your prism, and the figure on the right, which is your pyramid. But notice the shape of the base on both of these. Shape of the base on both of these is that they are pentagons. So it says using the figures to the right, what similarities would their cross-sections have? Well, cross-section is always taken parallel to the base. And if it's parallel to the base, it's going to take on the shape of the base. So since both of them have pentagons for bases, that means both of their cross-sections would be pentagons. They would definitely be similar in the fact that they're pentagons. But now the difference is if I took a cross-section of this prism, the first one, I know that all cross-sections will be congruent. They're going to be the same size going from the bottom all the way up to the top. It's not going to change. However, for the pyramid object on our right-hand side, the cross-sections will get smaller as you get closer to the vertex or to the top. They will all still remain pentagons. They just get smaller. So if they get smaller, we can think of these as being dilations. And so now, looking a little bit closer into our cones and our pyramids, we have a general cone, and again, it's a figure that has just a curved shape. Typically, our cones are going to be our circular cones. Pyramids, difference between that is that you have some sort of a polygon for a base. So on our right-hand side, we have a square pyramid, kind of like the ones in Egypt. Okay, so a cone with a disc at its base, that's your circular cone. That's what we will typically be focusing in on. Okay, general cone whose vertex lies in the perpendicular line to the base and passes through the center of the base is what's called your right cone. That's your ice cream cone. That's your typical cone that we know. Okay? Or it could be a right pyramid, kind of like the picture that we have up above. Okay, it just says depending on the shape of the base. So it could be a triangular pyramid if the shape of the base is a triangle. It could be a square pyramid if the shape of the base is a square. Okay, and then using this figure to the right, we're going to describe how the cross-section is obtained. Well, if you can take a look, these rectangular objects, these are trying to show you planes. So the one on the bottom, this is showing you this random curvy figure is sitting on this plane, this large plane. And when we take this cross-section, the planes are always parallel. So I could say I'm going to slice through with a plane parallel to the base. And when we do that, it says, what do you notice about figure B compared with figure B prime? Well, they look the same to me, it's just B prime looks smaller. So I could say, same shape, just B prime is smaller. So hopefully that's triggering some ideas here, saying that this is a dilation. And I could tell you that B and B prime are similar. Same shape, different size will always produce a similar figure. Okay, so the cross-section of a figure is a slice that's taken parallel to the base. In a cone, the cross section will always be a figure that is similar to that shape of the base of the cone. The vertex of the cone, if I'm thinking of it in terms of dilations, I can say is the center of dilation. Okay, so applying that here, and now we're going to go back and kind of get some information that we had from when we did our similarity and our size with our ratios and proportions. So it says in the following triangular pyramid, we have a plane that passes through the pyramid, so it's parallel to the base, and it results in a cross section. So this little guy that we can see here, here's our cross section. The area of triangle ABC is 25 millimeters squared. It says, what's the area of triangle ABC prime? Well, I'm noticing that they're giving us some lengths here. I can see that that's a side length of 3, and I can see top to bottom, the big pyramid is a side length of 5. Well, going back to our similarity chapter, we said if I know the proportion of the sides, so I could say the proportion of the sides, as long as I squared them, would be equal to the proportion of the areas. Okay, so keeping in mind a few things here, I can tell you that V, that's your center of dilation. I can also tell you, looking at these sides, I can tell you your scale factor or your comparison is going to be 3 to 5. Okay, so that, again, it's almost like our proportion of our sides, but we want to square it. So if I took our sides, side length of 3 and squared it, side length of 5 and squared it, or that's our scale factor, and we square the scale factor, that is equal to the proportion of the areas. So notice I'm going small to big. I don't know the small one. I do know the big one. Okay. So normally I would say cross multiply, but this is going to be even easier to solve because I can see, well, if I squared 3, I get 9, and if I squared 5, I get 25. So over here, it's hopefully very obvious what I know that x is going to be. X has to be 9 to make those fractions equal. So I could tell you the area of triangle A prime, B prime, C prime, it's got to be 9 millimeters squared. So that's a lot of the basics, vocab basics, applying. We're going to do some more work with this in class, but we got to be comfortable with the vocab and the different shapes and their names and their properties. So hopefully this was a good start, and we're going to practice some more in class. Have a great day.